Okay, today's lesson is on acceleration, the introduction to acceleration. So acceleration, here's the definition. It's just beautiful. We start off right away. Acceleration is defined as the rate at which velocity changes. The rate at which velocity changes. It's a nice mathematical term. We already know that change is delta. So how fast we change the velocity. As speed changes, an object speeds up or slows down. That's what speed changes over time. By definition, the object experienced an acceleration, an average acceleration. And here's our equation. It comes from Science 10 as well. Acceleration is the change in velocity divided by the time. I'm going to rearrange that for those people that like to see it in multiple ways. That would be the change in velocity is equal to a times t. Okay? We also get that time is going to equal acceleration over the change. Time is going to equal, almost there, the change in velocity over the acceleration. But my favorite format of that is just an expansion of this first one, is Vf equals Vi plus a times t. That we start off with the initial speed, add the acceleration times the time, and we end up with the final speed. Because the acceleration times the time is the change. So it's basically what we start with, Vi, plus how much we change. What you start with plus how much you change is what we end with. So this is a very nice version of the formula. Units for acceleration. The units for acceleration is meters per second. That's what the change in velocity is, divided by seconds. So algebraically, that's meters per second divided by seconds is meters per second squared. But what is a second squared? Never actually think of it as a square second. I would like you to be able to write this down as meters per second squared, but think of it as meters per second every second. A meter per second every second. A meter per second every second. I repeated it three times because it's very important. Pay attention here. We're going to do an example so that you understand this meter per second every second. Troy drives his moped. He accelerates from 2 meters per second to 7 meters per second in 10 seconds. So there's a lot of givens here. There's a 2, a 7, and a 10. So the initial speed is 2 meters per second. The final speed is 7 meters per second. And the time is 10 seconds. I've written down my givens. You write down the formula to calculate the acceleration, and that's the big boxed one up here. It says acceleration is change in velocity over time. So acceleration is Vf minus Vi all over t, because that's what the change in velocity is, Vf minus Vi. We're going to plug some numbers into it right now. So Vf is 7 meters per second minus 2 meters per second all over 10 seconds. The numerator becomes 5 meters per second, and the denominator is 10 seconds. Mathematically, this is 0.5, and algebraically for the units, it's meters per second squared. That's our answer of 0.5 meters per second squared. But here, let's try to understand what that 0.5 meters per second squared as an acceleration means. Okay? This is part of the question. What does 0.5 meters per second squared means? It means 0.5 meters per second every second. 0.5 meters per second every second, because I'm trying to teach you not to think of meters per second squared, but think of it as meters per second every second. So the initial speed, so when you started, the velocity of this moped was at 2. And it changed by 0.5 meters per second every second. So at 1 second, it's going to be at 2.5. At 2 seconds, it's going to be at 3. At 3 seconds, it's 3.5. Because every second, it goes up 0.5. Every second, it goes up 0.5. So we're at 6 at 8 seconds, and 6.5, and then 7. It had better end off at 7. It had better, because these were the givens. And what else is given? This timeline. We just had to figure out how it changed every second. And that's what we calculated. That was the answer for this question, 0.5 meters per second every second. That's how fast the velocity changed every second. Great example. Okay? Example number 2. Kelvin, quite a positive guy, accelerates from 10 meters per second, so there's a given, at a rate of 3 meters per second squared in his Ferrari. After 9 seconds, what is his speed? Okay, so we'll write down the givens. VI is 10 meters per second. The acceleration is 3 meters per second squared. And the time is 9 seconds. There's my givens. Write down the formula. Okay? The formula I'm choosing to write down is the one we were given above, but I'm going to write it in the format that I said was my favorite version of it. VF equals VI plus AT. Because that's what we're solving for. What was his speed? So initial speed is 10 meters per second plus an acceleration of 3 meters per second squared and a time of 9 seconds. 10 meters per second. Numerically, this is 27. And now just take a look at the units. Let's do these just so we understand. Meters per second squared times seconds. So this is going to be in the numerator. This second is in the numerator. And that cancels out with 1 of the seconds in the denominator of that one. So the end unit is meters per second, and that's what we wanted. We wanted meters per second there. So the end result is that VF is going to equal 37 meters per second. That's his final speed. Okay, digest it for a second. Think about it. We're given the initial and A and T. And A and T is how much it changes. How much does the velocity change? It's A times T. This A times T, let's just change to a nice... This is the change in velocity. A times T is how much it changes. So how much it changes is 27. So you start at 10 and you change by 27. So your final is 37. Okay? Now a unique way, a different way of teaching this introduction is I'm now going to introduce you to the formulas. I'm going to show you how they come about in another lesson, I'm just going to give you the formulas and let's just practice using them. There are going to be 4 formulas today, 4 distinctly different formulas. So all of chapter 1, we had 2 formulas. We had velocity is displacement over time, and we used it 3 different ways with average velocity, relative velocity, and just regular constant velocity. And the next other formula was t equals 1 over f, which is period is equal to the inverse 1 over frequency. In this lesson, I'm introducing 4 formulas. So double what we had in all of chapter 1. So let's just practice using these formulas. Mr. Curl is doing it a unique way. Let's just give you the formulas and practice them, and then we'll take a look at how important they are in a moment and how they're derived tomorrow. Okay, a plane is starting at 39 meters per second, accelerates for a displacement, a distance of 320 meters at a rate of 10 meters per second squared. Unfortunately, I put the equation at the bottom of the front side, and we're going to be working on this example right here. Okay, so we're going to use this equation, which is VF squared equals VI squared plus 2AD for examples 3 and 4. So let me just zoom in here a little bit more. Whoop, sorry, I didn't do that while I was recording. That was no silly. Okay, sorry for that miskey press. Here we go. Example number 3. Let's use this formula. Write down the givens. 39 meters per second is the starting speed. You can tell by the units. VI is 39 meters per second and accelerates for a distance of 320. How do you know it's a distance? You can take a look at the unit. Distance is 320 meters, and it's at a rate of 10 meters per second squared. Look at the units, you know that's an acceleration. 10 meters per second squared. Let's write down the formula. And the formula is VF squared equals VI squared plus 2AD. And the only thing we don't have is what VF is. So we'll plug in the numbers. VI is 39 squared plus 2 times an acceleration of 10 times a distance of 320. It already starts. Mr. Curl's getting lazy and not writing down the units. 39 squared is 1521. Plus 2 times 10 times 320 is going to be 6,400. So we get VF squared is equal to 7,921. So pulling out Mr. Calculator and square rooting that, you get VF is equal to 89 meters per second. Now there's going to be the question, shouldn't it be plus or minus because we're square rooting it? But we're starting at 39 and we're going forward in time. We're increasing by 10 every second. To go backwards in time would give us the negative. So we're smart enough right now that we're just going to rule out the negative. Okay, that's that question. Get a head start on number 4, and I will show you the answer in a few seconds. Have you got this far? Writing down the givens of 2, 10, and 2. 2 meters per second, 10 meters per second, and an acceleration of 2 meters per second squared. There's my givens are written down. And it's asking for what is the distance. So I'm just putting D equals question mark if that's what it's asking. And then I write down the formula. Now let's see if we can do the math. Try it out. Well, so far there's the math. 10 squared plus 2 squared. 10 squared equals 2 squared plus 2 times d. That becomes 100 equals 4 plus 4d. And this is where a lot of people, not a lot, there's always going to be 2 or 3 people with really poor math skills, or at least not a very strong math skill, will make this 8d. That's wrong. 96 is equal to 4d. And d is going to equal, sometimes people get 92 here by subtracting. It's supposed to be 96 over 4, which is 24 meters. Box off your answer. There is a great solution. Okay, here's the next formula. D equals vi times t plus 1/2 at squared. One of my favorite formulas, probably my favorite one of the kinematic one. Let's practice it. Okay? A car accelerates from 2 for a time of 4 seconds at a rate of 3 meters per second squared. How far does it travel? So the initial speed is 2 meters per second. The time that it accelerates for is 4 seconds. And the rate at which it accelerates is 3 meters per second squared. And we're asked for what is the displacement. A question right now for some people will usually ask, do I have to break down d equals question mark? No. Tomorrow you'll want to. I'll show you why you'll want it. But right now we won't do that. Won't force it. D equals vi times t plus 1/2 at squared. So d is, let's plug in the numbers, 2 times 4 plus 1/2, 2 times 4 squared. So this is going to equal 8 plus 24. So this is going to equal 32 meters. Okay? Let's just do a 10-second analysis of this. If you take a look at VIT, that's velocity times time. If you didn't accelerate and you're traveling at 2 meters per second for 4 seconds, you would have traveled 8. This is the distance that you would have traveled if you didn't accelerate. And this 24 is how much you did change in that displacement because of the acceleration. I wrote down 2, but I calculated with 3. I wrote down 2, but sorry. 3. Thank you. Let me highlight that. That was my blunder. I knew it was 3. I did the calculations with 3. Take a look. It's 4 squared, which is 16, times 1/2, which is 8, times 3 is the 24. I just wrote down that number wrong, but I did use the right number in calculation. Okay, so try example 6. Try example 6. We'll pause here for a moment and see if you can get to the answer. Did you write out the givens? Did you write out the formula? Now you just have to plug in the numbers. Give it a shot. Were you able to get 7 meters per second squared? Excellent. Okay. One more equation, 2 more practices. I'll leave that on the top there so you can copy it down if you need to. This is the 5th equation. The 4th one today. If you noticed, I started in equation number 2. We'll talk about why. A Ferrari accelerates from 2 meters per second to 14 meters per second in 4 seconds. What distance does the car travel in that time? VI is 2. VF is 14. And the time is 4 seconds. We're asked for the displacement. So we now write down the formula. D equals VI plus VF all over 2 times the time, how much it changes. So filling in the numbers, I get D is equal to 2 plus 14 all over 2 times 4. And that's going to be 16 over 2 times 4. That's just going to give us D equals 32 meters. 8 times 4. And here's the last question on this introduction to acceleration and all the different quantities and formulas. So give this question a head start. See if you can get the answer ahead of me. The answer should be 4 for 4 seconds. Try it out. Writing down the givens, the formula, plugging the numbers in. And now let's just simplify this. This will be 68 is equal to 34 over 2 times t. 68 equals 17t. T is just going to equal 4 seconds. Okay, we've done 8 questions here. We've learned 4 equations, 8 questions. Let's just take a look at the 8 questions. The 4 formulas. Okay, number 2 was called, and I'll write it as the acceleration is the change in velocity over time. It also had a different way of VF equals VI plus AT. You don't have to write this down. It's right there on the sheet. I'm just recapping it. Number 3 was VF squared equals VI squared plus 2AD. Equation number 4 was D equals VIT plus 1/2 AT squared, and the 5th formula was D equals VI plus VF all over 2 times time. Number 2 is the definition of acceleration, and 3, 4, and 5 are a few more equations that come out of it, out of the concept of acceleration. What is equation number 1? Why did I start at number 2? Because these are kinematic equations. These are all for motion. These are for accelerated motion. 2, 3, 4, 5 are accelerated motions. Number 1 is velocity is distance over time, speed over time. Speed is distance over time. There we go. That's the one we got from chapter 1. I'm just labeling them so because when we're tackling a kinematics equation, if there is no acceleration, we use equation number 1. If there is acceleration, then we can use 2, 3, 4, and 5. That's about it. Thank you very much. Smash the like button. Subscribe.